Let's start with the demonstration. Here you can observe the Opal-RT models designed in Simulink. The real-time simulation will run with 50 microseconds timestamp, so let's first talk about the physical models. Here you can observe the microgrid models are under the physical model block and the MP3 interface connections that are connected to the communication network model in EXataCPS. Inside the physical model block, you can observe all the physical components that make up the microgrid. We have the connection to the main grid, load 2 and load 3, and the shareable load that the main controller needs to shed when landing from the main grid. We also have the energy storage and the generator. On the left side, you can see the master controller with a function that is designed to shed the load when the received frequency from the outstation goes below 58.5 Hz, and the outstation that is providing the frequency measurements to the master controller. Going one step back, we can see the blocks needed to interface the physical models with the MP3 communication nodes that are in turn interfaced with the nodes modeling the communication emulation software EXataCPS. Now let's see the console of the experimental setup. In the console is where we are going to measure the frequency of the microgrid and all related measurement values such as the state of charge of the energy storage, the power output of generation, and other. Here is where also we are going to observe the impact of the time delay attack has in the frequency of the microgrid system. Now let's see the cyber layer or communication network model in EXataCPS. Here you can see all the nodes in the system, but the ones that we're going to focus in these demonstrations are node 1 and node 2. Node 1 being the master controller and node 2 the outstation of the shareable load. Let's start with the real-time co-simulation of the microgrid. First, we fire up the emulation of the communication in EXataCPS, and as you observe, all the nodes are reachable by the master controller. Now at the same time, let's load and compile the physical model of the microgrid in RT-Lab. After the loading and compiling of the model is completed, we can execute the model. At this time, the real-time co-simulation is running, and we have started to see data being exchanged by the MP3 outstation and the master devices. Currently, our microgrid is connected to the main grid, so you can see that the frequency measured does not vary and the breaker of the shareable load is connected. This is represented by the number 1 shown in the top block. Let's check the measurements in the scope. As you can see, the frequency is not very much since we are still connected to the main grid. Now let's island the microgrid from the main grid, and let's observe how this changes the stability. As you can see, now the frequency fluctuates more, and we can see it in more detail using the scope. It is important to mention that in order to show the impact of the time delay attack in our running real-time system, we designed the experiment in a way that the main controller will shed the load only when the frequency goes below a certain threshold, in our case 59.3 Hz, and will reconnect it when the frequency goes back to nominal 60 Hz. We understand that this may not be the way microgrid protection works in a real scenario, but for demonstration purposes, we designed the experiment in this way, so we can clearly show how well a time delay attack can affect the system and not permit the controller to shed the load due to the delay of the measurements received. That is why you see the frequency of the system fluctuating, and this is because of the shareable load being connected and disconnected of the respective thresholds. Now we can launch the time delay attack from the cyber layer of the EXataCPS, so we can go to attacks, modify packets, and load the 30 seconds time delay attack. Now we can just wait for the right timing to execute the time delay attack. The right timing will be when the frequency is going down, thus the shareable load is still connected, but the frequency measurement have not reached the shedding threshold. So we launch the time delay attack, and you can clearly see how the frequency keeps going down and the microgrid has been compromised to the point that damage to the equipment in the system could exist. The microgrid will need to go offline and the microgrid users will experiment a blackout.